In this lesson, we will discuss Jacobi symbols. So we will now discuss the Jacobi symbol, which extends the Legendre symbol from primes p to composite odd integers n. So can we set the Jacobi symbol a over n equal to 1 if x squared congruent to a mod n is solvable? And -1 if not. So while it might be tempting to define the Jacobi symbol this way, this would cause the important multiplicative property 3 of the Legendre symbol to fail. So for example, no, we can't define it this way. No, because the multiplicative property of property 3 of the Legendre symbol would fail. Here's an example. So x squared congruent to 2 mod 35 and x squared congruent to 3 mod 35 are not solvable. So 2 and 3 are not quadratic residues mod 35, and 6 is also not a quadratic residue mod 35. So, and neither is x squared congruent to 6 mod 35. So if we defined the Jacobi symbol the same way as we defined the Legendre symbol, then we would have 2 over 35 times 3 over 35 would both be -1, so -1 times -1 is +1, but 6 over 35, since 6 is not a quadratic residue mod 35, this would also equal -1. So if we define the Jacobi symbol the same way as the Legendre symbol, the multiplicative property will not follow. So in order to preserve this property, we're going to define the Jacobi symbol in the following way. So the Jacobi symbol a over n for an odd positive integer n and n is going to equal p1 times p2 up to pr, where all of the primes pi are odd. So the Jacobi symbol a over n for an odd positive integer n is defined by a over n will equal a over p1 times a over p2 times the product all the way up to a over pr, where the symbols on the right hand side are Legendre symbols. So first, a quick note. If n is prime, so if n just equals a prime p, then the Jacobi symbol will just equal one Legendre symbol, and so it just reduces to the Legendre symbol. Okay, so let's see an example of the Jacobi symbol. Let n be 135, which is 3 cubed times 5. Okay, so then when I evaluate the Jacobi symbol, say 2 over 135, I can rewrite this as 2 over 3 times 2 over 3 times 2 over 3, so I have a total of 3 factors of the Legendre symbol 2 over 3 times 2 over 5. And now we know how to evaluate these Legendre symbols. 2 is a quadratic non-residue mod 3, so we get -1 to the power 3. And 2 is also a quadratic non-residue mod 5, so this is times -1. And we have a total of 4 factors of -1, so this will equal +1. So notice that the Jacobi symbol 2 over 135 equals 1. However, 2 is actually a quadratic non-residue mod 135. And we can tell that because 2 is a quadratic non-residue mod 5, so it can't be a quadratic residue mod 135. So since 2 is a quadratic non-residue mod 5, it is a quadratic non-residue mod 135 as well. But the Jacobi symbol 2 over 135 equals 1. So the fact that the Jacobi symbol has value 1 does not imply that 2 is a quadratic residue mod 135. So thus the fact that the Jacobi symbol has value 1 does not imply that 2 is a quadratic residue mod 135. So if the Jacobi symbol has value 1, you can't automatically determine if you have a quadratic residue, but if the Jacobi symbol equals -1, you can be sure that you have a quadratic non-residue. In order for A to be a quadratic residue mod n, each of the Legendre symbols that make up the Jacobi symbol so each of the Legendre symbols A over pi, where pi is a odd prime dividing n, must have value 1. because if A is not a quadratic residue mod of prime, it won't be a quadratic residue mod a multiple of that prime. But A over n could equal 1 even though A is not a quadratic residue, mod n, if an even number of Legendre symbols A over pi have value -1, while the rest have value +1. But as I noted, the Jacobi symbol still can tell us if we have a quadratic non-residue, because if the Legendre symbol A over n equals -1, then A must be a quadratic non-residue mod n, because some Legendre symbol A over pi must have been equal to -1. So if the Jacobi symbol is -1, you can be sure that you have a quadratic non-residue. If the Jacobi symbol is +1, you can't tell for sure. So the next theorem will present the main properties of the Jacobi symbol that will help us evaluate Jacobi symbols. So let n and m be odd integers. I'm going to list 6 properties of the Jacobi symbol, and then we'll prove them. First, just like the Legendre symbol, if A is congruent to B mod n, then the Jacobi symbol A over n will equal the Jacobi symbol B over n. Secondly, A times B over n will be equal to A over n times the Jacobi symbol B over n. So the Jacobi symbol, the way we've defined it, still has this multiplicative property. And the next property is unique to the Jacobi symbol. If you have a Jacobi symbol A over n times m, then this is actually equal to A over n times the Jacobi symbol A over m. Fourth, this is the same property when we have the Legendre symbol with -1. For Jacobi symbols, the Jacobi symbol -1 over n will still equal -1 to the power n minus 1 over 2. 5, the Jacobi symbol 2 over n will equal -1 to the n squared minus 1 over 8. So we see that the Jacobi symbol 2 over n will still equal 1 if p is plus or minus 1 mod 8, and we can determine that 2 is a quadratic non-residue mod n if n is congruent to plus or minus 3 mod 8. And the final property, which is the law of quadratic reciprocity for Jacobi symbols, So we have that if the greatest common divisor of m and n is 1, so m and n are relatively prime, then the Jacobi symbol m over n times the Jacobi symbol n over m will still equal negative 1 to the m minus 1 over 2 power times n minus 1 over 2 power. So the Jacobi symbols m over n equals n over m when either m or n is 1 mod 4, and if both of m and n are congruent to 3 mod 4, then these symbols are negatives of each other. So the proofs of these properties follow from the corresponding properties for Legendre symbols. So let's see the proofs. So for the proof of 1, let n equal p1 times a bunch of other primes up to pr. And if A is congruent to B mod n, then A must be congruent to B mod each one of the prime factors of n. So mod pi for all I. Then A over pi must be equal to the Legendre symbol B over pi for all I. And therefore, the Jacobi symbol A over n, which is A over P1 times A over PR, will equal B over P1 times up to B over PR. That just equals the Jacobi symbol B over n. So now for the proof of part 2, again let n equal P1 up to the product of P1 up to PR. Then A times B over n, by definition of the Jacobi symbol, would be A times B over P1 up to A times B over PR. And since these are Legendre symbols, I can break these up as A over P1 times B over P1 all the way up to A over PR times B over PR, but I'm going to group them together. So we're going to have A over P1 up to A over PR, and we also have B over P1 up to B over PR. But that's the definition of A over n times B over n. So we see that the Jacobi symbol also has this multiplicative property. Now for property 3, I'm going to let n be P1 times up to PR, and m is going to be the product of primes Q1 up to QS. So the PI and QIs are odd primes. Then the Jacobi symbol A over NM is the same as the Jacobi symbol with P1 up times PR times Q1 up to QS in the bottom. By the factorization of n times m. And then we can, by definition of the Jacobi symbol, we can break this up as a over p1 up to a over pr times a over q1 up to a over qs. But this just equals the Jacobi symbol a over n times a over m. So that finishes part 3. Now property 4 is a little more involved. So let n equal p1, the product of p1 up to pr. Then the Jacobi symbol -1 over n will equal -1 over p1 times up to -1 over pr. And since these are Legendre symbols, we can write these as -1 to the p1 minus 1 over 2 times up to -1 to the pr minus 1 over 2. So this is a property of Legendre symbols. And if I combine all these factors of 1, we get that the Jacobi symbol -1 over n will equal -1 to the sum I equals 1 to r of pi minus 1 over 2. So I'm just adding up p1 minus 1 over 2 up to pr minus 1 over 2. Now I'm going to use a fact about odd integers. So notice that if I have two odd integers, p and q, so for p and q odd, if p and q are odd, then p minus 1 is even and q minus 1 is even. Therefore, p minus 1 times q minus 1 will be congruent to 0 mod 4, because p minus 1 is even and q minus 1 is even. And if I expand this, I get the congruence pq minus p minus q plus 1 will therefore be congruent to 0 mod 4. If I add p plus q and subtract 2 from both sides, I get pq minus 1 is congruent to p plus q minus 2 mod 4. And then finally, if I divide both sides by 2, I'll have to reduce the modulus, and I get that p times q minus 1 over 2 will therefore be congruent to p minus 1 over 2 plus q minus 1 over 2. And I've reduced the modulus by dividing by 2, so this is mod 2. So from this last congruence, we see that if you raise -1 to either side of this last congruence, you'll get the same number, because these two quantities are congruent mod 2. So how am I going to use this? Well, I'm going to rewrite the exponent on -1 up here. I'm going to rewrite this by repeating the fact that I just proved in the last congruence. So by repeating this fact, we see that the sum I equals 1 to r of pi minus 1 over 2 will be congruent to the product of the p's, p1 up to pr minus 1 over 2 mod 2. Therefore, negative 1 to the sum on the left will be equal to negative 1 to this one fraction of the product of p's minus 1 over 2. Thus, the Jacobi symbol negative 1 over n will be equal to negative 1 to the n minus 1 over 2, because remember, n is just the product of these p's. So that finishes the proof of part 4. Now the same technique is going to be used to prove property 5. We need a slightly different congruence and that we're going to repeat to get the exponent to look the way we want it. So let's see the key step of the proof of part 5. So the proof of 5 is essentially the same as the proof of 4. We need a different fact, so accept that using the fact that if p is odd, then p squared is congruent to 1 mod 8, we can obtain the congruence p squared minus 1, the quantity p squared minus 1, times q squared minus 1 will be congruent to 0 mod 64. So then, again, if we expand this, we'll get p squared times q squared minus p squared minus q squared plus 1 is congruent to 0 mod 64. And by rearranging this, we get p times q, the quantity squared, minus 1 will therefore be congruent to p squared plus q squared minus 2 mod 64. And if I divide everything by 8, we get the congruence that we will need for the proof that p times q, the quantity squared, minus 1 divided by 8 is congruent to p squared minus 1 over 8 plus q squared minus 1 over 8 mod 8, but also mod 2. So using this last congruence and the formula for the Jacobi symbol 2 over p for a prime p, we can finish off the proof of property 5 for the Jacobi symbol. So for property 6, we're going to assume the law of quadratic reciprocity when the entries are primes. So now we're going to prove that it's also true when m and n are just odd numbers. So let m equal p1 up to pr and let n be the product of Q1 up to Qs for odd primes Pi and Qi. Then we're going to use the fact that m and n are relatively prime So since the GCD of m and n is 1, let's start with the Jacobi symbol product. So m over n times n over m. By definition of the Jacobi symbol, this will equal m over q1 up times the product up to m over qs times n over p1 up to n over pr. And now I can use the properties of the Legendre symbol to break up the factors m and n. So this, I'm going to get a lot of factors here. So m over q1, I can write that as p1 over q1 up to the product of pr over q1. So that is m over q1. And I do this for each of the m over the q's until I get up to p1 over qs times up to pr over qs. So now I've broken up all the m over q's. I need to do the same thing by breaking up the n over p's. So I get q1 over p1 up to qs over p1. So that would be n over p1. I'm going to do this for each one until I get up to n over pr, which will be q1 over pr times up to qs over pr. Okay, so now we have the product of all the Legendre symbols with all the possible p's over all the possible q's and all the possible q's all over all the possible p's. So I'm going to regroup these in order to use the law of quadratic reciprocity for Legendre symbols. So I'm going to write P1, Q1 next to Q1 over P1. And I can do this all the way up to PR over QS times the Legendre symbol QS over PR. And I'm going to use the law of quadratic reciprocity for each pair of these Legendre symbols. So the first pair will equal -1 to the P1 minus 1 over 2 times Q1 minus 1 over 2 power. And I'm going to do this up till the last pair, which will be -1 to the power PR minus 1 over 2 times QS minus 1 over 2. And what we'll see is that I can rewrite this as -1 to the power the sum I equals 1 to R of the PI minus 1 over 2s times the sum J equals 1 to S of QJ minus 1 over 2. And just as we saw in the proof of property 4, these sums are congruent to m minus 1 over 2 and n minus 1 over 2 mod 2, so I can replace them. This would be negative 1 to the power m minus 1 over 2 times n minus 1 over 2. So this was just as in the proof of property 4. We saw that the sum from I up to R of pi minus 1 over 2 will be congruent to m minus 1 over 2 mod 2. So I can use this to replace the exponent with m minus 1 over 2 and similarly with n minus 1 over 2. So this finishes the proof of the 6 main properties of the Jacobi symbol. And now I'm going to do a couple of examples of evaluating Jacobi symbols using these properties. First, let's evaluate the Jacobi symbol 107 over 137. Well, by the law of quadratic reciprocity, I can rewrite this as 137 over 107 because 137 is 1 mod 4, so I can just flip it without introducing a minus sign, so that's by property 6. Then I can reduce 137 mod 107 to get 30 over 107. So this is by property 1 of the Jacobi symbols. And 30 is 2 times 15. So this is 2 over 107 times 15 over 107 by property 2 of the Jacobi symbols. And 2 is a quadratic non-residue mod 107, so I can replace using the formula of property 4. We get this equals negative 1 times the Jacobi symbol 15 over 107. And then I'm going to use the law of quadratic reciprocity, and 15 and 107 are both 3 mod 4. So if I flip this Jacobi symbol to 107 over 15, I have to introduce a negative sign, but that will cancel with the other negative sign, so this becomes plus 107 over 15, again by the law of quadratic reciprocity. In reducing mod 15, I get this is 2 over 15 by property 1. And the Jacobi symbol 2 over 15 equals 1 by formula 5 for the Jacobi symbol. So notice that we started out with the Jacobi symbol 107 over 137. It turns out that 137 is actually prime. So 107 over 137, you can think of it as a Legendre symbol, and since the answer was plus 1, we can still say that 107 is a quadratic residue mod 137. So since 137 is prime, we can say that 107 is a quadratic residue mod 137. So it's interesting, we can still use the properties of Jacobi symbols to evaluate Legendre symbols, and if we started out with a Legendre symbol, we still can deduce quadratic residues or quadratic non-residues using the final answer. Now I'm going to evaluate the Jacobi symbol 4,567 over 12,345. 12,345 is 1 mod 4, so by the law of quadratic reciprocity, I can flip this without introducing a negative sign. This is equal to 12,345 over 4,567. This is by property 6. Now I can reduce mod 4,567 to get 3,211. This is by property 1. Now by the law of quadratic reciprocity, this will equal the negative 4,567 over 3,211 by the law of quadratic reciprocity, and reducing using property 1, this is negative of 1,356 over 3,211, again by property 1. And now I'm going to factor 1,356 as 2 squared times 339. So this will equal the negative of 2 over 3,211, quantity squared, the Jacobi symbol squared, times 339 or 3,211. Again, by property 2, since 1,356 equals 2 squared times 339. Now, any Jacobi symbol squared will just equal 1. So this just equals the negative of 339 or 3,211. I can use the law of quadratic reciprocity again, and both of these entries are 3 mod 4, so when I flip it, I have to introduce a minus sign by property 6, and reducing mod 339, I get this is 160 over 339 by property 1. I can factor 160 as 2 to the 5th times 5. So this will equal 2 over 339 to the power 5 times 5 over 339 by property 2. Again, because 160 is 2 to the 5th times 5. And using property 5 of Jacobi symbols, we see that the Jacobi symbol 2 over 339 will equal negative 1. So this equals negative 1 to the 5th power times 5 over 339. And then by the law of quadratic reciprocity, I just have negative 1 times the Jacobi symbol 339 over 5, and reducing mod 5 gives me negative 4 over 5, but 4 over 5, 4 is a perfect square, so this will just equal the negative of 2 over 5 squared by property 2. The Jacobi symbol 2 over 5 squared will be 1, so this answer will just be negative 1. So the Jacobi symbol we started with has value negative 1. So the answer is negative 1. We can therefore conclude that 4,567 is a quadratic non-residue mod 12,345. If the answer was plus 1, we could not determine whether it was a quadratic residue or not, because the bottom entry is composite.